Dimensional analysis is something that looks overwhelming and looks intimidating, but really is supposed to be designed to be something simple. It's supposed to be a tool that you can use to figure things out really easily. And when you get later in chemistry, this comes up because we will convert from a starting amount of chemical to a final amount of chemical. And if you can ignore the math on that, it allows you to see what's happening chemically. So I want to go through dimensional analysis, but I don't want to just show you an example and work through. I want to kind of try and provide you with some of the theory and some of the purpose behind it, as well as I want to show you some tips into why you might not be understanding what to do and how to kind of work through that. Now, I like to call dimensional analysis multiplying by 1 with a twist. Right? And you know from math that if you multiply any number by 1, that you get that number again. It's unchanged when you do that. So in dimensional analysis, what you're going to do is you're going to multiply by two values that are equivalent to each other. Okay? And if the two values are equivalent, that's the same thing as kind of like multiplying by 1. You're trying not to change the amount. Okay, so if I have so many grams and I want to know kilograms, I don't want to change the object, I just want to change how I'm reporting out. Now, if we do something like feet and miles, we could say that our conversion factor is going to be 5,280 feet is equivalent to 1 mile. What I'm saying there is that these two things are equal to each other, so the ratio of them is kind of like a 1. The number is not 1, the number is 5,280 to 1. And the units are not 1. So in isolation, these two things are different. But combined, 5,280 feet is equivalent to 1 mile, and so those are two equal values. And so I'm trying to change the numbers in units without changing what I'm doing. Okay? So what I want to do to that then is I want to set up a structure that makes this really simple for me to do. Let's look at a really simple example. If I told you that I baked 4 dozen cookies, and then I said, well, how many cookies is that? Okay, you can probably shout out the answer without me doing anything else. Okay? But how do you do that? Well, what we're doing here is we're kind of following a series of processes. Okay? First thing you want to do is whatever information you're given, you want to find what's called the given. Okay, you want to find the thing that has a number and a unit with it. In this case, it's 4 dozen. You want to write that down. Okay? Then, you want to draw a set of bars like this. But we'll talk about what they mean in a second. Whatever units you have here, you're going to copy down here. Then, the units that you want to end up with, in this case I want to know how many cookies I have, go up here. That process of writing things down like that is kind of the basis of dimensional analysis. And the purpose of that is that I can do that without thinking. I can write down the given, I can copy its units and put the new units there without really understanding anything. And so it sets up my math for it to be solved without me really having to expend a lot of effort. And when I get a more complicated problem, that's going to be beneficial. The last thing you want to do is you want to make these two amounts equivalent to each other. This is your 1. So cookies and dozens, how do I put two numbers there that make those equivalent? Well, 12 cookies is 1 dozen. They don't have to be those numbers. It could be 24 cookies and 2 dozens. But it has to be a ratio that gives us a unity. And from there, I've set up my math to be solved. Now, going back, I said we would talk about what these lines mean. When you see a vertical line like this, this means to multiply. So it's going to be 4 times 12, and then there's nothing here, but times 1. And when you see a line like this, that's going to mean to divide. So I'm going to do 4 times 12 divided by 1. I'm going to kind of group all the numbers by themselves together. 4 times 12 divided by 1. And then for the units, I'm going to do dozens times cookies divided by dozens. Well, dozens divided by dozens cancels. So my units are just going to be cookies. And so what I've set up there is 4 times 12, that's 48 cookies is my conversion. And that's the answer, of course. Okay, so we're all familiar that 4 dozen would be 48 cookies. So that's a simple problem. But when we go through and do more complicated problems, this process is going to allow us to kind of avoid thinking. And there's a lot of problems that you can actually take advantage of for using this. So in the beginning of the year, a lot of times you'll do metric conversions. So if we take something like 14 centimeters, and I say convert that to decimeters. Okay? My given is 14 centimeters. I would copy my units. I would put my new units up here. And then I would fill in numbers, decimeters and centimeters. I could put in 1 and 10. I could put in 10 and 100. As long as the two amounts are equivalent, it's fine. Then I'm going to bring all the numbers together. So I've got a 14, a 10, and a 100. So this is going to be 14 times 10 divided by 100. My units are centimeters times decimeters divided by centimeters. So these will again cancel. And I will be left with 1.4 decimeters. Now, if I had chosen 1 and 10 here, then it would have been 14 times 1 divided by 10. It would still give me the same answer. Okay? If I go through and I give you something that's a little more obnoxious, and I say, okay, what about same problem for the starting point, but what if I wanted to know kilometers? Okay, well, I don't necessarily know how many centimeters in a kilometer. Of course I do, but I want to build some suspense here. But I do know very easily how many centimeters are in a meter. So I can do a conversion, and then I can do a second conversion and go from meters into kilometers. And that will work just fine as well. Again, I set this up without having to think much. At this point, all I need to do is plug in numbers to make these equal. 1 meter and 100 centimeters, 1 kilometer and 1,000 meters. So now I have 14 times 1 times 1, which is going to come out to 14. And on the bottom, I have 100 times 1,000. That's 100,000. And then for units, centimeters times meters times kilometers divided by centimeters times meters. The centimeters will cancel, the meters will cancel, and I'm left with what I want, kilometers. So this would end up being 0.00014 kilometers, or 1.4 times 10 to the minus 4th kilometers. Okay? Now, again, metric, you might have a staircase or something that allows you to do that just by counting decimal places. There are other things you can use this for. So if I told you that you have a 2-gram object, let's actually make that 2.0 grams, get our sig figs going a little bit better. And I told you that the density of that object was 8.0 grams per centimeter cubed. And I said, what's the volume in centimeters cubed? That's something you could do with an algebraic manipulation. But you could also use dimensional analysis. 2.0 grams is your given. That density is a conversion factor. This is saying 8 grams per centimeter cubed. Now, per is one of the things that a lot of people have missed in their schooling. What does per mean? Per means per 1. This says that 8 grams of the material is equivalent to 1 centimeter cubed of volume of that material. So there's an equivalency. There's a 1 here. 8 grams, 1 centimeter cubed is a unity. Okay? So I can use that as a conversion factor. I can plop grams down here, centimeters cubed here. Well, 8 goes with grams, and 1 goes with centimeters cubed. If you're familiar with the video, there's a guy who drove around and he asked his girlfriend Chelsea if he were to drive 80 miles an hour, how long would it take him to go 80 miles? And she doesn't get this concept. And so she sits there and struggles through trying to explain what that would be, and going through all sorts of various things. Now the guy thinks it's funny and thinks, how could you not know 80 miles per hour? That she can't make that connection. But the reality is most people never really get a chance to look at that when they're young. And afterwards we take for granted that you sat down and thought about that. So keep that in mind when you're doing this. Now, I have 2 times 1 divided by 8. That will come out to 0.25. And then my grams will cancel. And I'm left with cubic centimeters. And that would be my volume. I could have gotten the same result by doing a math problem, but this involves less thinking. Okay, I don't have to do any manipulations. I just, boom, plug, and I'm done. Now, the last one, let's say you have to do something obnoxious. So you get to class, your teacher says, I'm driving 70 miles per hour. What's that in meters per second? Okay, my initial reaction to that is I just don't want to do it. That sounds long and boring, and I know I can get an answer, but I don't really have the patience or the will to do it. It sounds like busy work. Well, now you can respond back by making that back into busy work. 70 miles per hour means 70 miles per 1 hour. And I want to convert that into meters per second. Okay? So this is a good example of this process. So I want to change miles into meters, and I want to change hours into seconds. Let's start with the hours, because that's going to be simple. So hours in seconds. How many hours and seconds are equal to each other? Well, 1 hour is 3,600 seconds. 60 times 60. Okay. Miles to meters is going to take some effort. Miles, I can change to feet. Because I know that 5,280 feet is 1 mile. Feet, I can change to inches. 12 inches is 1 foot. Inches, I can change to centimeters, because 1 inch is 2.54 centimeters. And centimeters, I can change to meters. Now, while that looks like a lot, that wasn't particularly challenging for me to get down. And now I've set up a very simple problem. I'm going to do 70 times 1 times 5,280 times 12 times 2.54 times 1. And get all of that together and put that on top. So 70 times 1, which is the same, 5,280 times 12 times 2.54, divided by 1 times 3,600 times 100. And when I get that out of a calculator, it comes out to be 31.3. And then for my units, I have miles canceling, I have feet canceling, inches canceling, centimeters canceling, I have meters left. And then hours cancels hours, and I'm left with seconds. So I have my units of meters per second, and that would be my answer. Okay, 31.3 meters per second. Now, one thing to note when you're doing these for sig fig, when I'm starting at the beginning here, I have 70 miles per hour. That's 1 sig fig. A lot of people will look in the middle of this and they'll see various amounts of sig figs. The thing to keep in mind though is that 1 hour is exactly 3,600 seconds. It's not a measurement of 1 hour, it's an equivalency. And that makes this exact. It means it's 1.0000 forever. This has infinite sig figs, as does this. And so typically only your measurements in these are going to count, and a lot of times your measurements are only going to be the number at the beginning. There are exceptions to that. If we go back to the density problem from before, I was using a density that's probably a measured quantity, and so therefore that sig fig would come into play. But typically, a lot of these conversions will just have conversion factors in the middle, and those will have infinite sig figs. So whatever you start with, you should end with. So my final answer would be 30 meters per second is equivalent to 70 miles per hour. Okay? So that's the purpose behind dimensional analysis, and that's what you can use it for. You can use it as a systematic way to solve problems. It's going to be very convenient down the line, and it's going to help you not have to think as hard about the math components when you get into chemistry things that are difficult to understand.